Go ahead, please.
Yeah. So, hi everyone. So, my name is Jason. I'm a first-year graduate student here. And my area of interest is actually topology and differential geometry. So, so here's a fun fact. So I just took my differential geometry class this morning, and we just defined all sorts of things in Calculus 3, which is this class, in a more general sense. So we are doing kind of different calculus on Euclidean spaces like R1, R2, R3. But what I'm doing is that we are doing those calculus in different spaces, in more complicated spaces like a torus, like a sphere, things like that. So this class actually is a starting of a lot of things, and it actually has a lot of applications to engineer and things like that. So I think it's an interesting class. So anyways, thanks for the opportunity for me to teach here. And just a word in front, which is I tend to speak kind of very quick when I get excited or nervous. So feel free to stop me, and if I get too excited or like if you have any questions, that's all fine. Yeah. So let's get to math. So on Wednesday, I was sitting in the back row, and I learned that. So we talked about Green theorem. So just a reminder of what Green theorem is. So Green theorem is this kind of beautiful theorem about how you can integrate line integral by other means. So if you have a domain D in R2 and have a function f, the line integral of f along the boundary of this region is the same as integrating the circulating density, the green operator of f, over this region D. So here I want to point out that the boundary of this D has some orientation, which is that imagine you are standing on this region next to the boundary, then the boundary should be on your right and the region D should be on your left. So it is, in this case, it is oriented counterclockwise. Yeah. And so here's the formula for the Green theorem. So you have line integral on the left, but here on the right you have an integral over the whole region here. And the intuition is that circulating f around the boundary of D is the same as accumulating the circulation density over the region D. Any question about this concept from Wednesday? Okay, so today my goal is to help everyone to digest this concept by applying this theorem to some concrete example. So let's get started. So here's the first example. So imagine there's a circle that's oriented clockwise, so it's going this way, and we have a function which is kind of complicated. It's e to the power of x plus y in the first entry and tangent y plus 3x in the second entry. And then we want to compute this line integral of f along this circle. Okay? So imagine we are living in a world like 2 weeks ago, or in a world without Green theorem. What will we do? Well, what we can do is to do the standard way, right? We need to parameterize C and then parameterize f in terms of the parameterization of C, and then do the line integral in that way, which is kind of troublesome because this is a very complicated function. You may get something very annoying if you're trying to parameterize everything here. But now we have this Green theorem. So what we can do is that we have a circle that's oriented clockwise, and Green theorem is about relating the line, the curve, to the region bounded by the curve. So how can we relate this circle to the disk oriented by this circle here? Well, we can take, so we know that this C is oriented this way, so C minus, as we learned from line integral class, that C minus is the curve that's oriented oppositely. So let's take C minus. And then if we consider the disk here, we see that in this way, C minus is actually the oriented boundary of the disk here, because if you imagine you are standing on the disk next to this boundary, then the boundary is on your right, and the disk is on your left. So C minus is the oriented boundary of this disk. And this kind of relates C minus to this region here by Green's theorem, and then we can relate C minus and C from our knowledge in line integral class. So here's the specific calculation. We can go through step by step. So we want to calculate the line integral of f along C, but that's the same as calculating the negation of the line integral of f along C minus. So calculating the line integral of f in this way is the same as the negation of calculating the line integral of f in this way. That's what we learned in line integral class. And then C minus is a boundary of D, so that's just a replacement of C minus with the boundary of D. And then by Green's theorem, we know that the line integral of f along the boundary is just the same as the circulation density of f over the region D. So that's the Green's theorem. And now we can just apply, like recall the definition of the Green operator. That's the derivative of q over with respect to x minus the derivative of p with respect to y. So we can substitute that, and we see that this tangent y actually doesn't matter because we're taking derivative of this complicated function with respect to x. So that's just 3. And the same holds here. The e to the power of x term doesn't matter because we're taking the derivative of y with respect to y. So that's just 1. So overall, we have that we reduce this line integral of f along C to integrating a constant function over the region, over the disk here. So that's the same as like taking the product of this constant with the area of this region, which in this case is a disk, is a unit disk. So the area of it is just pi by the formula of the area of a circle. So what we get here is just minus 2 pi. So the idea here is that if you see some curve that's bounding some region, you can try to use Green's theorem to relate the line integral of the curve of the boundary with the integral of the circulating density about over the region here. And then that may simplify a lot of things, as shown here. So, any question about this example and the idea of relating the line integral of the boundary with the integral of the region? Okay. So we'll apply this model to another similar example. So this time, again, we're given a curve C, and C is made up of like line segments from 0, 0 to 2, 2, 2, 2, 2, 2, 0, 2, 0 to 0, 2, 0 to 2, 0, 0, and we have a function. And then we'll compute the line integral of f along this curve. So I have drawn this this line here. So this kind of butterfly shape curve is a C here. Okay, so imagine we are living in a world 2 weeks ago, or like a world without Green's theorem. Then what we're gonna do is to parameterize f with respect to this curve, which will have 4 components. We'll first integrate f in this way, and then this way, and then this way, and finally in this way. So we'll have 4 integrals if we just do the line integral right away, which is kind of annoying. But now, since we have Green's theorem, we can consider like the region bounded by this curve. So we see that this curve is actually consists of two parts. First is the left wing of this butterfly, so that's D1. And then we have the right wing of the butterfly, which is D2. So what I denote here is the left component and the right component. And then we see that the left component is just the oriented boundary of D1 using the rule, like using the imagination rule I just talked about. And the right component is not the oriented boundary of D2 because the orientation is kind of opposite. So again, we can just take the minus version of it. So this curve minus is the boundary of D2. Or in other words, this curve is a boundary D2 minus. And then we just carry out the same computation. So this reduces the line integral of this whole thing to the line integral of this plus the line integral of this, which further reduced to the integral over D1 plus the integral over D2 by Green's theorem. So we can just carry out the similar stuff as example 1. So here's the full computation, which I can just quickly go through it. But that's basically the same as what I just said. So the line integral of f along this butterfly curve, we break it into two parts, the left part and the right part. So the line integral of f along the left part plus the line integral of f along the right part. And that's the same as the line integral of f along the boundary of D1 plus the line integral of f along the minus version of the boundary of D2. And then we know from the property of line integral, as example 1 shows, it's just the minus of the line integral of f along boundary of D2 by basically taking minus to here. And then here we can just, so we have two line integrals along two boundaries. So we can apply Green's theorem here. So here we can do like we can take the Green operator of f and integrate that over D1 and do the same for the right part. And again, we can substitute the Green operator by its concrete definition. So that's that, and it's the same here because we are taking the Green operator of the same function, so these are the same. And now we see that these two derivatives are just constants, it's 9 and 9. And then integrate the constant function over some region is just taking the product of the constant function with the area of the region. So it's 9 times the area of the left part minus 9 times the area of the right part. But the area of the left part and the right part is the same. They are symmetric triangles. So that gives us 0 in this case. Yeah. So just to summarize, the idea is just to relate a given curve to the region you are bounding. That's the key idea of applying Bray's theorem. Any question about this example and the key idea here? Okay. And now, these are just two kind of basic examples of Green's theorem. And now I want to move on to talk about two kind of more significant applications of Green's theorem. So the first thing I want to talk about is area. So as our previous computations show, we see that the line integral of a curve, where the curve is bounding some region D, is kind of directly related to the area of that region if the circulating density of that f is constant, right? Like after we reduce everything using Green's theorem and taking a derivative, if this is something constant, we can just multiply this thing with the area of the region. So the line integral is directly related to the area of the region. And the question is, can we do this backwards? So suppose we want to know, suppose we are given a region instead of a curve, and we want to compute the area of that region. Can we find some function f so that after applying Green theorem, we can reduce the problem of finding an area of that region to finding the line integral along its boundary? Because Green's theorem works like this way and also the opposite way. What we are doing is to using one direction of Green theorem. I want to apply it backwards in this time. So here's what I claim. We can consider f equals 0x, so 0 in the first entry, x in the second entry. I claim that the area of the region D is the same as taking the line integral of f along the boundary of D. And here's how it works. So area of D is just taking the integral of 1 over the region. And this 1 is the same as the derivative of x with respect to x minus derivative of 0 with respect to y. So, and this is indeed the Green operator of this f here. So this is Green operator applied to 0x. And then this is something on the right-hand side of the Green theorem. And then we can convert it to the left-hand side, which is the line integral along the boundary. So this is the same as integrating 0x along the boundary of the region. And then that's by definition of line integral, this is the same as integrating x along the boundary of D with respect to y. So we see that we kind of turn a problem of computing the area of a region to a problem of integrating some function along the line integral. So why is this helpful? Well, we can